In this section, I will introduce how to do the preprocessing. Okay, so the first step is realignment. We also call this step as motion correction. When you're collecting the data, it will take about half hour, and the subject may move their head or their body a little bit, so the location of their head in the scanner may change. You cannot avoid movement because the subject are living, right? They need to take breaths, and even if they take small breaths, they are moving. So the big movement will impair your data quality, but the head small movement are acceptable. The goal of this step realignment is to adjust a series of images so that brain is always in the same position. So means they move, but we move their head back by manipulating our images. Okay, so before you do the realignment, make sure, right, you follow the last step for the data preparation. Now, in the analyst data subject folder, you will have 540 data in each ROM folder and 1 data in the T1 folder. So all of the data are aligned to the AC/PC line. So open your SPM, open your MATLAB, set the current directory to this folder, the subject folder, and then we open the SPM fMRI. Okay, so click this button, Realignment. Choose the last one, Realign and Unwarp. So the batch editor appears. Before you do realignment, right, make sure you didn't do it before. This is the clean data. You just dump the reorientation. Otherwise, your image will be reoriented twice, which may be not accurate. Okay, so we have 2 ROMs, and then we need to click here to fill out our data, to click the new session twice. And here you have space to define your 2 ROM. And for the first ROM, first image is highlighted. Click specify and go to click the ROM 1 folder, select all, done. And then go to the here section, the next one, specify, go to the ROM 2 folder, select all, and done. So you're done of our setup. Keep other options as the default setting. So here, one we may need to revise for other data set is here, where is your reference image, means the register to which images. Here we select the default to the first image, because in the following step we want to co-register your EPI image to your T1 image. And in our sequence, right, we collect T1 first, and then we collect two runs of T1 images. So the first image of the first run is the closest image, right? Just right after we collect T1. So we use this one with the reference. As the reference means the movement between T1 and the first EPI image is the minimum across the time series. Okay, so that's it. We click here, the run batch. That's easy, right? But it takes several minutes to run. So after you click batch, okay, something appeared here. Okay, we finish how many percentage? So the computer is estimating the head movement across time. So for the motion correction, right? STPM use 6 motion parameters to describe the head movement. They have a model called grid body transformation. Assume the shape and the size of two volumes, means two images, two brains, should be co-registered, are identical. It means it is the same brain. And so one volume can be superimposed upon other by a combination of 3 transformations and 3 rotations, representing its movement related to the reference image. Here we can see, right, is the estimated head motion parameters. So you can see here we have X transformation, Y transformation, and Z transformation. There's 3 parameters for the transformations. Means move the entire image along an axis in the space. X means move left or right. Y means front or back. Z axis means up or down. So this is in absence of rotation. And also we have the other 3 rotation parameters. First one is X and Y yawn, and X and Z roll, and Y and Z pitch. So this parameter are in the absence of translation. So here we can see the first 540. The x-axis is the number of images in the. This is the first one, and then we have 1,060 in total. This is the first half is run 1, and this is run 2. And the y-axis is how far they moved. So usually if the movement is in, 3 or 5, within 3 or 5 times of your voxel side, it looks good. So in this current study, our voxel is like the unit of each image, right? It's the minimum 3D cubic that of your image. So our head motion is not big. Within each ROM means it's good. So if you have motion between ROMs, it's acceptable. But if you have big motion within each ROM, it's not good. Means your brain moves a lot. So means for one location, sometimes it's gray matter. Sometimes if we move, it may change to white matter, or it may change some tissue outside your brain, right? Area outside your brain, if it is not brain, just air or something, means the signal change dramatically. This is not good. Okay, so it will take several minutes to run. So something showed up, but right, you don't need to care about. We just wait for several minutes. So here I have a case of head motion parameters. For example, here on the x-axis, the maximum motion is 1 point something millimeter. So it's not big compared to its voxel size. It's just, this is acceptable. And also you see here the subject is very stable, right? Within each ROM, just have very minimum movement. That's very good. But for the location, right, in your dimension, the subject may move. The row is X and Z, right? May move a little bit, 2 degrees, but it's also acceptable. Means the data, and also you see within each ROM, it's very stable. Means the subject is very good. So we just mentioned we have 6 parameters, right? 6 motion parameters, 3 for transformation, 3 for rotation to estimate. So here you will see the information completed. You have to see it 6 times, and then we can finish this step. Okay, reslicing images means it's writing the output. We are almost done. It's done. Right here it's done. So after you run the realignment, you can check for each run right? You have some new files called UF, prefix UF something. They are realigned API images, and with 540 new files for each ROM. And also you have a TXT file, text file with RP underline F something. If you open this, it has some numbers. So you have 6 columns of numbers. They are estimated head motion parameters with each line for each image, right? Each row is for one parameter. Also, you have a PDF file, .ps file here with the name of today's date. If you open, it saved all of everything showed up in the graphic image. The first page is the realignment, estimated the parameters. Looks good. Also, you have a min API images in the ROM1 folder. So if you go down here, you have the min UF something. Here, this one is the average across all of the 1060 images. We need this image for the following process. Okay, we are done for the realignment. The next step is coregistration. The purpose is to alignment the alignment of function, means the API image, and the structural image, means the T1 images, from the same subject to map the functional image into the anatomical space. Because in our data analysis, the final goal is to see which region activated, right, during a certain task condition. So we need to know which structure is activated. To do this, you click here, coregistration, and then click the last one, estimate and reslice. So something appeared in the batch editor. Here we select the reference image, means the image that assumed to remain stationary, as the min image. So we have the min image in the ROM1 folder. We have too many images. It's hard to find the min image. That's fine. You click this sign, and min means the file name should be set up a filter to just select the file name the file began with min, right, something. So yeah, we have only one image appeared. Select here, click this. So we select one image and click done. The source image is the T1 image, the structural image. Go to the T1 folder, click select this one and done. And we don't have any other images, something. So after this, we press run. Okay, it's running. Also takes some time. Okay, something appeared. Right, it's done. So here it's done. So here, the toolbox gives us a graph of the co-registered images. So here you see here, this is the main API image. This is a structural image, right? See here, so their shape are the same. The brain are at the same location. So the origin point is the AC line aligned to the ACPC. If you click top, right here, the cross set also move to top. If you click the boundary, right, you move around the image to see whether or not they are in the same shape, in the same location. Looks good. We're done. So after this step, if you go to the T1 folder, you will see here a new file appears called RS something. This one is the coregisted image, means this we rotate T1 to make the brain at the same location as the main API image. We need this image for the following processing. The next step is the spatial normalization. The purpose, we know that human brains are variable in their size and shape. So the ultimate goal of the spatial normalization is the spatial transformation of brain into a common space, making them comparable to each other. So I want to emphasize that the following step is specified to our data set because we want to normalize our data to an age-specific space, which is not the space usually used for fMRI study, because we are running the adolescent study. We want to get the spatial information more accurately. So if you want to analyze the adults data, means other data, please check the SPM manual page 248 to 251 for the new spatial normalization recommended by the SPM 12. So to do this, right, to the sample data, we want to co-register the API image to a to our template. So let me copy the template first. Okay, so now for the sample data, I create a folder called template. Here I have one image called the ANTS 14 years old 3T brain bias corrected. This is from another public data set. So if you want to know where does it come from, check our paper for this project. Okay, how to do the spatial normalization? So click batch. Not here. Here is for the new spatial normalization approach, which is recommended for adults data. So here we need to click the batch, SPM, utility, and no utility, tools. Go to the old normalize, and then select the old normalize, estimate, and write. So click subject twice because we have two runs of API images, and here the source image is the one we need to use it to match the template. So here this is the co-registered T1 image. Click the RS something in the T1 folder. Also the same for the ROM2, also select the RS something in the T1 folder. And for the subject 1 here, image to right, click the ROM1 folder, the triangle. And then we want to select all image with or realigned image, means with the prefix as UF. So press return to apply the filter, and then select all. Make sure you are selecting 540 images, not 1080 images. Done. Okay, do the same thing, but here we are working on the ROM2, RF, hit return, select all. Done. Here we need to select the template image and then specify. Go to the sample data folder. Here you have a folder called template. Select this one. Done. Keep other setting as default. Run. Okay, it's running. So here, this is the template, and this is our image after the transformation. So here, to make our image look similar as the template, you can move your cursor around to make sure, right, whether you have any problem. If their shape looks pretty different, means you have some problem for the normalization. Okay, it's done very quickly. Now we are going to do the last step of the pre-processing, called the spatial smoothing. So the purpose of smoothing is to filter out the high frequency regions in each volume, with the aim to increase the signal to noise ratio in images. And also, we want to reduce the noise in the image and to reduce the effect of anatomically variability, which is failed to correct during the spatial normalization, and is a prerequisite for the statistical analysis, such as Gaussian random field needs. This is for the first level modeling. So to do the spatial smoothing, the purpose is just make the image more blurry, but we satisfy some spatial resolution, but to increase our signal to noise ratio and to reduce the between subject variance. Okay, click the smoothing or the between images variance. Images, we need to do it for 2 ROMs specifically, right? So first click ROM 1. So after normalization, you have some new files with the prefix as W. You have new 550.ni images with the prefix of W in each folder, each ROM's folder. So here we use those normalized images to do the smoothing. So here to use the filters to select all images begin with W, select all, make sure the number is 540, done. And here make sure we change the number to 666, because in our study we are focusing it is optimized for detecting the activation in the ventral striatum, which is our regions of interest in our study. If you are doing pre-processing for other datasets, just keep the default setting and press the green triangle. Default setting is 88888. So if you want to change this, make sure you have a reference about how to change and why to change. Okay, press. It's running. Okay, it's done. Let's do it again for round 2. Images to smooth. Select images begin with W. Select all, done. Change to 666. Press run. Okay, so we are done of all the pre-processing. Not difficult, right? So here, after the smoothing, right, you can see some new files with the prefix as S in each ROM folder. So they are smoothed data. We can show all of the data, process data together to see what's the difference between the steps. And so if you want to show multiple images in one simultaneously, right, you can click here, check registration. For example, ROM 1, we want to click, this is the realign the raw data, and with prefixes U is the realigned data, with W is the normalized data, and with S is the smoothed data. So we can show them simultaneously. See here, so realignment, right, doesn't change the shape, but maybe change the location slightly, because I'm showing the first image, which is the reference, it didn't move, so the realigned data and the raw data looks the same. And here is the normalized image. So see here, the shape of the brain changes to make it similar as the template we used. And here is the smoothed data. So the shape are very similar as the normalized data, but it looks more blurry, right? So this is the difference. Okay, we're done for the pre-processing. So in the next section, we are going to introduce how to prepare your behavioral data.